So welcome to the seminar today, and our speaker today is Nima Lashkari, whom we all know from his work on several works at the interface of quantum information and quantum field theory, especially. Well, he has also worked on the emergence of gravity from quantum information earlier, and then he worked on how to compute the modular Hamiltonian excited states and several other ramifications. So today he's going to tell us about his new project on understanding normalization as quantum error correction. So over to Nima.
Thank you so much for the invitation and the introduction. So yeah, today I'll be talking about renormalization group flow and connections with approximate error correction, classical and quantum. So the topic of the talk is going to be pretty conceptual, and I will walk you through a set of examples. A lot of what I will be saying is going to be, well, some of it has appeared already in this work with my student Keiichiro Furuya and Shoei Youssef, who is here. And also, there will be a follow-up paper with Keiichiro and Mudassir Musa, who joined us as a postdoc recently. There will be more coming up. And yeah, so please feel free to stop me at any point. It's going to be a conceptual talk, but hopefully there will be explicit examples. The examples are mostly going to appear in this paper. The discussion in the very first paper is mostly formal. A lot of it is in the language of operator algebra and operator algebra quantum error correction, which might seem a little bit difficult to work with for a physicist, but hopefully the second paper includes a lot more examples, and we're going to go over the examples today. All right, so there will be 4 parts to the talk. There will be an introduction, which at high level discusses what are the connections between renormalization group and error correction. Then we will talk about an example, which is Kadanoff spin blocking, just classical real space renormalization group. By the way, even though the connection between RG and error correction goes beyond real space RG, in this talk, I'll be mainly focused on real space RG. So I'll not be doing any Euclidean momentum RG or anything like that, but there will be a story associated with that. I'm happy to talk about it offline. So we'll be talking about classical RG as spin blocking, then the quantum version thereof, which is multi-scale renormalization ansatz, MERA, and a continuous version of it, which was proposed for quantum field theory. So we'll be working out the details of error correction, approximate error correction, and these. So that's the plan of the talk. So let's start with the error correction, introduction. So error correction codes. What is the idea of error correction code? We have a system. There's a Hilbert space that we want to simulate. There's a Hilbert space K of the system we want to simulate. We encode this Hilbert space of K in some larger physical Hilbert space H. For example, we encode a single qubit in n qubits using some isometry, some encoding isometry. We want this to be an isometry so that it properly preserves the inner products and so that it preserves the information we encode in. Otherwise, it won't be an encoding. And of course, to be able to correct for errors, we should be able, this physical Hilbert space has to be much larger than the amount of information that we encode in. So where we have encoded the information is a subspace called the code subspace. That code subspace is basically WW dagger. This is a projection in H that projects you to where you have encoded your information. Clearly, anything that does not act on this code subspace is something that does not corrupt, could be interpreted as an error that cannot corrupt your encoding, right? So if some operator acts from 1 minus pH and sends states to 1 minus pH, your encoding is immune from such perturbations. with respect to such perturbations. So there could be understood as noise. All right, so we are interested in many-body many-body systems, classical or quantum. So what we have in mind is some arrangement. So the physical Hilbert space is an arrangement of qubits, for example, and the errors we would like to correct for are local perturbations, right? So we would like that's the feature that we would like. That's the desirable feature. And as we just said, for an error, actually, for the error to be correctable, it has to satisfy the following property, that E of A, some operator, some error operator that I act here. Sorry, are there questions? Oh, okay.
Oh, I have to just mute people. Sorry.
Okay. If you apply this WW dagger, it's just proportional to the projection to the code subspace, which means that once you project to the code subspace, this noise disappears, right? So this is the idea behind error correction. We'll talk more about this. All right, so now a renormalization group flow. The renormalization group flow is, in spirit, a similar idea. We have a physical Hilbert space, which is the UV Hilbert space with many degrees of freedom. Let's just talk spin systems. So let's not worry about quantum field theory yet. Spin systems, so they have a lot of degrees of freedom here, and HIR has less degrees of freedom. They supposedly correspond to the long range degrees of freedom. And there's an encoding, which is an embedding of HIR inside HUV. This embedding is basically the renormalization group flow, actually the inverse of the renormalization group flow. It's the map that takes you from the infrared to the UV. Now, WW dagger is a projection that projects down to the long range correlations, long range degrees of freedom. And the idea is that an operator or a local operator is an irrelevant operator if it satisfies the following property. It just means that once you project it to the code subspace, the irrelevant operator disappears. So it's irrelevant. And the picture to have in mind is renormalization group is, instead of like a two-step thing, is a multi-layer map. So instead of having one W, you have many successive application of Ws, and at each step, you coarse grain by a little bit, right? So for example, you have a bunch of, let's say here you have 9 spins. At each step, you coarse grain 3 of them into one emergent infrared degree of freedom, right? And then in the next step, you coarse grain further to 1 degree of freedom, right? So these are like successive Ws that you're applying to go from IR to the UV. And the idea is that some local perturbation here down the chain, as you go up the chain, will basically its effect will disappear. We'll see that, well, what will happen is that its effect is going to get exponentially weaker, right? But in the limit of repeating this many times, local perturbations approximately go away as you project the code subspace. So this is some high-level conversation. Yes.
I have already a question here. So this as you said, it's only an approximate equality that this isometry acting on the irrelevant operator is proportional to the projection. But if it is, but you cannot invert it up, right? If you just, it is exactly equal to the projection. The fact that it is invertible requires that it's not exactly the projection, no?
No, actually, no, that's not an issue. So if it's exactly the projection, it means that you have an exact error correction code, right? So when it's approximately a projection, it means it's an approximate error correction code. Well, we'll go through this actually. If I don't answer your question, please ask me. The statement about
my question was simply that if you have this the relevant and irrelevant operators do mix, right? I mean, it's so the fact that you could yeah, anyway, probably you're going to talk about it in
I'll discuss some of these issues. All right. Yes.
Yeah, so if we are moving from the higher degrees of freedom to the lesser degree of freedom, so we are not losing information right here.
No, we are losing information because
So
yes,
then how do we recover the information from the renormalization group method?
because okay, the idea is that what you recover is only the infrared information, which is not the whole thing, right? So to have something like error correction, you encode a single qubit in many qubits, and you do this, of course, redundantly. This map is redundant, and this redundancy is essential to be able to correct, right? If this projection is the whole Hilbert space, nothing is going to satisfy this equation, right? So I think the confusion might have been caused by the fact that you're thinking of continuous quantum field theories. Let's just think of discrete systems where literally the number of degrees of freedom in the infrared is less than the number of degrees of freedom in the UV. And now there is room for error correction. We'll spend a lot of time talking about the continuum limit, but yeah.
Okay.
All right, so now let's just talk a little bit more about connected more with physics. That was very high level. Let's just talk a little bit more in detail. So let's consider a renormalization group. What are the possible endpoints of renormalization group flow? Because we said that the HIR is our code subspace, right? Roughly speaking, so this is like a rough picture I'm gonna give. It's not an exact story, but I just want to sort of, it's suggestive. As you do renormalization group flow, your system might end up in a unique vacuum or a degenerate vacuum. You might have degenerate vacuum, right? So roughly speaking, I want you to think about degenerate vacuum as exact error correction and near unique vacuum as a story of approximate error correction. So this is an analogy, all right? We're going to go further. So when you have a unique vacuum, you could have a mass gap, like in the continuous limit, you could have a mass gap or some sort of scale invariant fixed points. So both of these cases are going to be, we're going to spend some time talking about. But this side of the story is actually more well known. The connections between quantum error correction as an exact error correction and degenerate vacuum of quantum in classical or quantum system is sort of a well-known story. So you could have degenerate vacuum due to two reasons. You could have spontaneous symmetry breaking or topological order, right? So topological order famously does give you quantum error correction. And spontaneous symmetry breaking also gives you classical. So this is important. This side is classical error correction. This side is quantum error correction. So we'll go through some examples. And in spontaneous symmetry breaking, you could have discrete symmetry or continuous symmetry. Of course, you will have massless Goldstone mode here, and so on and so forth. So here you're going to have like a harmonic oscillator as your classical information. Sorry, harmonic oscillator as the encoded bit. And this is going to be just a bit, classical bit. But this is some high level, again, picture, and then we're going to zoom in more. So as I said, the code subspace in exact error correction analogy with RG is going to be the subspace of vacua, right? So when you have spontaneous symmetry breaking, you end up with classical error correction code. And when you have topological order, you end up with quantum error correction code. So notice that in this story, there is, once we do flow all the way to the vacuum, there are no real local degrees of freedom left. We're just talking about the vacuum, right? This is, we've just gone all the way to the vacuum. So examples. Consider a 1D classical Ising model. The ground state, there's a Z2 symmetry. The ground state spontaneously breaks this Z2 symmetry. So we're in this setup where you have discrete symmetry breaking. And the ground state is going to be, either all spins up or all spins down. This is a repetition code. Basically, you have encoded a single bit, classical bit, into two states, two ground states of a many-body quantum system. You've encoded one bit in many bits, right? And why is this an error correction code? The reason is that if you perturb a local error, you could easily catch that. You could totally test for the you could detect this and it could be corrected. Notice that the correction has to be done. It's not like the system is completely immune to errors. You need to correct. You need to actively correct. But there will be a you could detect these errors and correct for them. And the idea is that errors accumulate. Larger scale errors are going to be exponentially suppressed by the size of the errors, because these are independent local errors occurring. So the possibility for an error to flip all the spins at the same time is very, very tiny.
Nima, can I ask
Yes.
something here? So
Yeah.
these errors are correlated, right? Because they're not independent. Because
No, I'm imagining as independent errors.
Yeah, but there's a correlation that we know that there are ground state correlations.
So
these are
the
not
correlations are in the code states you have prepared.
Mm-hmm.
The errors are independent. So you see, these are my two states, the code subspace I've prepared. On this code subspace, errors occur, right? And now errors occur because of interaction with the environment, blah, blah, blah. And those the action of the error is completely independent. This is actually how, roughly speaking, we encode in like.
Maybe I can ask you. Suppose if you have this two-dimensional system, we have this Mermin-Wagner, right? So we know that these kind of perturbations are going to destroy the ground state completely.
Very good. That's my next point. So this is impractical. The reason is that finite temperature immediately breaks this stores a symmetry, right? So there is no phase transition, and this code I just said is not stable towards finite temperature perturbations. And this is impractical because we are never really sitting at the ground state level. So this is a code, but it's not a very good code. So we need something more. We would like this to be a finite temperature phase transition that will make sure that below this transition, these states are actually protected, right? So yeah, exactly. So you would like the spontaneous symmetry breaking to survive up to some critical temperature. And if that is the case, we call that self-correcting memory. So in D = 2, the two-dimensional example, you actually have a self-correcting memory. That's what we would like. That's a desirable feature. Did I answer your question? So indeed, in one dimensions, the moment you turn on temperature, these kink anti-kink perturbations will just destroy your code. But in finite temperature, D = 2, for example, these are protected. So it's the idea of finite temperature, some sort of barrier separating these two ground states.
Yeah, but yeah, I sort of understand, but what I still don't get is it very important that what happens if you have a BKT phase transition in the first place?
If I have a
BKT phase transition.
BKT.
Where this coastal is a two-less type phase transition, where there is no local order, but the two-point function changes its characteristics.
So yeah, so I'm using, so the situation could be a lot more complicated than what I'm describing. I'm just giving you some sort of a cartoon picture of how it could be related, and I make my model more and more complicated as I go forward, right?
Yeah. So actually what you're trying to say, there is some scale like the temperature or say the correlation length, which makes these errors approximately independent. I think that's what we're trying to say.
Absolutely. And we'll see that in the context of local error correction. We're going to see that.
And okay, so what you're assuming that but the examples that I'm talking about doesn't fall in this class. So you're saying that if you as long as there is some scale that some correlation length, then this is fine. Okay.
Yeah, exactly. That's the picture. So at the moment, my discussion is so basic that I have not gotten into local error correction, but we'll get there. All right.
Sir?
Yes.
Sir, I have a small clarification in the previous slide.
Mm-hmm.
So is there any reason why we call the fixed point of the RG flow as vacuum, or
No, these so fixed point. So what I meant here, I meant the low energy. So if you have like if you have take a low energy limit. So yeah, I haven't gone all the way to the vacuum. The vacuum is unique, so it will be boring to talk only about the vacuum. So we talk about low energy states, and low energy states, the gap closes. So I have a continuum of states. So here in this picture, indeed, I'm not only talking about the vacuum, because the vacuum is just single state, that's boring. I'm talking about low energy subspace.
okay, yeah, thank you.
Sure. All right. So that was just some simple analogy for classical codes. Now let's talk about quantum codes, but these are exact. We're still on this side of the story.
If I may just quickly
Yes.
interrupt.
Yes.
So, and just to clarify what you were saying in response to Ion's question, that if you do have correlated errors, then the problem of error correction becomes much more difficult, right?
For sure. I mean,
so we normally just assume that is one reason why we assume that our errors are the Markovian process.
Exactly. So, I mean, at the end of the day, every error correction code is designed to protect for a class for an error model, right? So the idea is that what I'm trying to say here is that in local quantum system, as you go to a low energy, uncorrelated local perturbations are noise that are naturally protected by the state given to you.
Right.
That's what I'm trying to.
There's no such thing as universal perfect error correction.
Yeah. Sure. So I guess we're not going to talk about these things in detail. We're going to talk about approximate error correction, but just to give you another example, let's talk about quantum codes. So I said that for degenerate vacua, to get quantum codes, you have to have topological order. So let's just give an example of that. The example would be the toric code. So the toric code is a 2D lattice with on each edge you have qubits, and you consider two sets of operators which are on edges. You put x, x, x. These are for a particular vertex v. You consider this for local operator, and you consider these BP operators. These are plaquette operators, and basically, for a Hamiltonian that looks like this, so it's a local Hamiltonian, it's clear that if you look at the vacuum of this Hamiltonian, the vacuum is going to be given by these a four-dimensional vector. Sorry, I should clarify. So I said this is a 2D lattice. I'm interested in the case of where the 2D lattice is a torus. So there's some topological, there's some non-trivial topology, so that I have non-contractible loops. These loops, right? So and then these loops are gonna these loops are gonna be where the encoded information is. So here, what we're doing is that we're encoding 2 qubits in the state of, for example, n squared. Well, actually more than that. Anyway, so the whole lattice of this whole lattice of qubits, right? So we're encoding this redundantly and in such a way that for this Hamiltonian, the states of interest are going to be the ground state, right? And what are we protected against? We're protected against noise that acts locally. Any operation that acts locally, noise here, we're going to be protected against it, because we could, again, by the same principle, we're gonna there will be some procedure to look for symptoms of errors, and if you detect them, you correct them, right? So you actively have to correct for errors. As exactly analogous to the D-Col1 Ising model that I gave before, the example I gave before. Again, this is unstable at finite temperature, and it means that this is not, I mean, the terminology is that it's not self-correcting, The moment that you turn on finite temperature, this code isn't really working. But then there are other versions of this. So there is a 4-dimensional version of the toric code that is actually topologically, stable to thermal fluctuations. Now there's a 3-dimensional version. There's a 3-dimensional topological codes that's protected against that is stable in finite temperature, but the stability is not the barrier, the potential barrier is not as high. And so this is a long story that we're not going to get into, but I just wanted to mention.
Nima, just to interrupt again, sorry.
Yeah.
The toric code is stable at temperatures which are below the correlation length of your torus, right? Am I mistaken about that?
The below the correlation
meaning that, like, your lattice has a certain size, and so if your fluctuations are not large enough, then the errors are exponentially
no. So what I was saying is that there's no finite temperature phase transition in this setup. So to find this 4-dimensional, said differently, the moment that you turn on temperature, this I guess degenerate vacuum space goes away. There's no, well, sorry, I should be careful about this. Well, I should be careful with this. So it's about how large of a barrier, energy barrier do you have, right? So when we talk about self-correcting quantum memory, we usually have some standards for how large of a barrier should we have. But yeah, there in the terminology, in the story of quantum memory, this is not going to be important for us because I'm just giving an example in passing to advocate the connection. But yeah, there's a long literature on this. There's like tons of stuff. This is an active area of research. But this is not, we're not concerned with this. What we're concerned with is this part, approximate error correction. But
yeah,
I
wanted to get some connection with what you're saying. In the case of topological, the low energy dynamics is given by some topological field theory. Typically, say we can also talk about say fractional quantum Hall systems in this context. So in that case, you have the one way to see this would be that you have this quasi particles and quasi holes, and they have a non-trivial braid group, right? And,
absolutely.
So how do you put that in? I mean, your code subspace would be the entire space of this this quasi-particle quasi-holes with the braid group. And,
so people have looked at these. There are many. What I'm saying here is just a simple model, but people have looked at models with all levels of sophistication, and there's enormous literature on this. I personally never worked on this topic, but it's a big discussion. Here I'm just giving an example to motivate, right? So, but the discussion that I'll be having mostly in the remainder of the talk is going to be about approximate error correction. So this was to say that if you want exact error correction, you look at degenerate vacua. And this is not the topic of our talk, but that is a connection between RG and error correction. So now we get to the story that we want to discuss, which is even in a system with ground state that is unique, the low energy subspace has some approximate error correction code properties. Indeed, if your system has degenerate vacua, what you're going to end up with is a mixture of classical and quantum codes. Such mixtures exist, and they naturally come up in the language of operator algebra quantum error correction. If that is not familiar, it doesn't really matter, but yeah. By the way, I just, for people who are interested in holography, I just wanted to make the comment that in holography, we have a mixture of classical and quantum codes. So that's sort of important. But all right, so now let's talk about what we said before. So we're looking at the low energy subspace of the low energy. We're looking at the low energy Hilbert space, which is, these are the Hilbert space of low energy degrees of freedom, long range degrees of freedom, and this is going to be our code subspace. So now we're gonna motivate this by an example from classical spin blocking, right? So again, let's take D equal 1 classical Ising model on 3 n sites, for example, and we're going to put nearest neighbor and some on-site energy. So these are the couplings, G and H, and so S variables are plus minus ones, and these are like all sorts of different states combinations that you could have for your 3n qubits. That's 3n bits. So of course, we're interested in the thermal partition function. That's the state that we're going to do the RG on. And a simple RG prescription, a simple coarse graining scheme is to block 3 adjacent spins into a single degree of freedom using majority vote. If the addition of 3 adjacent sites, site 3i, 3i minus 1, and 3i plus 1 is positive, we're going to say that the effective degree of freedom is plus 1. And if it's negative, if it's not positive, we're going to say if it's negative, we're going to say it's minus 1, right? It's just a simple coarse graining thing. This is all classical, right? So I could use vector space notation to just denote this. Notice that this is, I mean, it's not quantum mechanics, but I can still use vector notation. So I can think about the ket or the state that is describing these 3 bits, right? So 3 bits that is being mapped to a single bit. So this is the S prime, and this is the 3 S's, degrees of freedom. And there's a matrix. There's a matrix that does the job. And you could just construct this matrix from this. It's just, it's that the T transpose is going to be your encoding map, right? So T is the map that coarse grain, and T transpose is the map that encodes this S prime effective degree of freedom back in the physical long range, short distance theory, right? So, okay, this is the encoding. So far, we're just talking about the encoding. And of course, you're going to have 3n sites. So you're going to apply this Tn times every time to go to the next layer. And the encoding is going to be T transpose tensor n times coming down, right?
Just
so
a stupid question.
yeah.
I mean, maybe this is a very stupid. So this T is not really invertible, right? Because you get one.
No, it's not.
There'll be many. Yeah.
It's a co-isometry. It's a co-isometry.
So basically, what you mean is the subspace that you're talking about.
Exactly. So this is it's.
Because normally I thought encoding means that you take 1 bit and then you embed it in a larger Hilbert, but still there's a 1-to-1 map. But here this doesn't seem to be a 1-to-1.
No. I mean, no. Sorry. This is the W dagger. So my T is this W dagger.
Mm-hmm.
So W that I was talking about encoding is T transpose. T transpose is a map. Yeah. Of course, if you have an isometry, and if you restrict the range of the isometry, you get the unitary, then it becomes 1-to-1, right?
Yeah. No, I have a really stupid question. So my question is as follows. Suppose normally when you define encoding, like you take 1 and you map it to say a 3-qubit system, but there is still a 1 unique state that corresponds to the up bits, right?
Yeah, but that's you're saying there's a unitary map between your system simulating system and your code subspace.
Exactly.
Code not the whole thing.
Exactly.
Right?
Yeah,
so,
exactly.
If you talk about the whole thing, there will be a projection involved.
Right. But here I do not understand what is exactly the code subspace because if I take 1, just say the top bit, what is it being encoded into?
T transpose of I can write it explicitly. It's just like it's a state. You could write it down. It's actually it's pretty straightforward to write this down. So there will be 2 particular states of 3 bits that are given by this. You could work it out. It's just a two-dimensional subspace.
My confusion is with the definition of T itself, because you said that it's given by a majority vote, right?
Yes.
So basically, you mean that it goes into a superposition of all of that, all of these states.
It's really complex composition, but yeah.
Okay. Sorry. Okay, now I understand.
Yeah, this is classical physics. I'm just using vector notation so that it's suggestive. It's really classical physics. So these matrices are all like real things. It's just like probability matrices. But anyway.
Okay. Okay. Thanks. Sir.
Sure. So now this is the encoding. What we would like to for this, so we would like to ask whether this encoding, this is your renormalization group flow, right? Classical renormalization group flow. We would like to ask whether this is protecting us. This is protected, the encoded states deep in the infrared are protected against local errors. So how are you gonna discuss local errors? A very simple model is this a classical channel that flips the bit with probability p and probability 1 minus p, it does not flip a bit, right? So this is like a quantum operation. Sorry, it's a classical operation. It's a classical version of a quantum operation, right? It's just a classical channel. It's a conditional probability distribution. So this is the error that we're applying, for example, here. And to see what this error does to up here, up the chain, you just have to apply this TT transpose and move this up, this error up the chain. So it's just a simple exercise. You do this, you move this up the chain in one step, you multiply these matrices. You see that after one step, so of course, after one step, this corrupted one bit here, and here it will corrupt one bit as well. So if you start with a local operator, it will remain local. A local perturbation, it remain local. But the important feature is that when you do the you move this up, instead of the probability of error being p, all of a sudden it's p over 2. So the error has become weaker after one step. And indeed, as you repeat this, the error every step becomes weaker and weaker. And after many steps, it's actually exponentially weaker. So some perturbation that you threw in here under RG is just becoming weaker and weaker. Now, what we would like to argue for is not just local perturbations, but also we would like to talk about non-local perturbations, non-local errors as well, but non-local errors of finite extent, finite support. So let's just track the evolution of a non-local operator under renormalization group. In the first step, so there are two stages to the process. If there's a non-local perturbation that acts on 6 bits here, in the next step, this just pollutes 2 bits. In the next step, it pollutes 1 bit, right? So if you start with a gigantic error, an error with gigantic support, in the first stage, the support of this shrinks exponentially fast until it reaches a single site. During this phase, the error is not getting weaker. If you do the calculations, you see that the error is not getting weaker under this flow, but the support is shrinking. Once you hit a single site, the stage 2 begins. In stage 2, the error gets weaker with every layer. So basically what we find is that there's this structure that there's this hierarchical structure that every perturbation, non-local perturbation, slowly shrinks to a point, and then it gets weaker and weaker. So you k local errors become local, one local after k log k layers, and after that they just get weaker and weaker. So if you go sufficiently far in the infrared, you're approximately immune from such errors. This is the basic idea in the simple example. Are there questions about this?
Can I ask one question?
Yeah,
can you
sure.
go to the initial the previous slide? Can
Yes.
you explain the 2 to the power of 2?
Yeah. So, all right. Sorry, the power of 2 or this p over 2?
The last line, last matrix.
Oh, this one. Yeah. So after one step, the probability is split in half. So what you would like to do is you would like to apply the, so think of this map phi of G1 tensor I23 as T at this map, right? This is phi. What you're doing is that you're applying phi many times.
But
Right?
we are grouping the three spins. So shouldn't it be 3 to the power?
Sorry?
We are grouping 3 spins.
Yes.
So I thought it's a 3 to the minus 1.
No. This factor of 2 does not come from the 3. This does not come from the 3 spins. It's just a simple, like this is a very simple calculation. There is a majority vote. You construct the matrix that corresponds to this, and you apply it, and you obtain it. But let me just try to. I will actually try it in a. I can try to explain a little bit what's going on. Maybe it's helpful to say it now. So what is going on is that this is a classical channel. A classical channel has a spectrum. It could leave operators invariant. There could be operators that are in the fixed points of the errors that are in the fixed points of the operators that are in the fixed points of the classical channel, the RG channel, RG as a classical channel. Then such operators will survive in the infrared. Those are going to be some logical operators for us. However, generically, if the vacuum is unique, there will exist no such operators. This classical channel actually has all eigenvalues that are so the real part of the eigenvalues is going to be as positive, which means that as you take any operator here, there will basically all decay as you apply this. If you have a map that sends positive things to positive things, and it has no fixed points, basically what it does to any arbitrary positive thing is that gradually flows this to the unique invariant state. But maybe this will come clear in the quantum example. This here is the only thing is that this factor of half has to do with the eigenvalues of this this classical channel, classical RG channel. It's a very Heisenberg picture. It's a Heisenberg picture for RG.
Okay.
So that was a classical example. There's a quantum version of this, which was first worked out, to my knowledge, in this paper of Isaac Kim and Castoriano from 2017. And I'll be summarizing it here in the light of this discussion that we had. So in quantum real space renormalization group, what we do is very similar to the Kadanoff's spin blocking that we just discussed. So here we're going to spin block 3 spinners into a single spin, emergent degree of freedom. However, there's one new ingredient, which are these unitaries, these local unitaries that are called disentanglers. And it's an essential step in quantum mechanics. In classical physics, you don't need such a thing. But in quantum mechanics, you need to get rid of these local entanglement in your renormalization group. This stage is the same. And what is considered to be the encoding is the combination of these two together. So our W is V dagger, U dagger, right? Which is an isometry. So this is the encoding that takes us from the Hilbert space, at this scale. This is the Hilbert space of 3 qubits to this Hilbert space, whatever number of qubits that we have here. And this is a map that we're going to repeat many, many times. This is the basic of what is called multi-scale renormalization ansatz, or MERA, that was, to my knowledge, was first introduced by Gifford Vidal. So this is exactly analogous to the discussion that we had. There will be a channel. We're going to think about this renormalization group flow as a channel that moves operators. You could move operators up the channel, which is how that corresponds to renormalization of a particular operator. So if you insert an operator here, this on the renormalization group map will renormalize in the following way. O will go to OWW dagger, right? So that's the action of this operator in the next layer, and the next layer, and the next layer. So this is what we discussed so far was a renormalization as a classical channel, and this is going to be a quantum version of it. It's a quantum channel, as I just said, right? So we would like to again say that this local error in the infrared just disappears. And the idea is exactly what I said. This is this is a quantum channel, and it will have a spectrum. So there will be eigen operators, right? And then there will be lambda i's. Now, because it's a quantum channel, these lambda i's are going to be all sorry, I think with my notation, all negative. Real part of them is going to be all negative. So there will be, if you have fixed points for these quantum channels, these operators will be preserved. They will not change. And such a thing will lead to degeneracy of the vacuum. But if you don't have such thing, which generically for generic coarse graining, you won't have it, then the real part of these guys is going to be positive. So these operators get weaker and weaker. These lambda i's are the things that in Mera ends up being the conformal dimension of conformal primaries. So when you have a fixed point, as you flow these operators, the eigen operators correspond to conformal primaries, and these guys end up being the conformal dimensions. But I guess we don't need to talk about it and be very precise. Here, what the analogy goes way beyond that. And notice that the choice of coarse graining, in Mera, there's always a choice to be made, which is about what are these W's, what are these unitaries and V's. And we often view this as a variational ansatz. But whatever the choice is, that corresponds to a particular choice of a quantum channel. And this quantum channel has a spectrum, and this story works for it. So exactly in parallel to the classical story, there are two stages. If you talk about the renormalization group of a large operator, there are two stages. In the very first stage, just based on the structure of the geometry of this tensor network, a large operator here, the support of it in the very first stage shrinks until the support reaches a single site. Then stage 2 begins, where the operator starts getting weaker and weaker because how does it fall off? How does it get weaker? Exponentially, and that exponential could be upper bounded by the real part of the first eigenvalue of this quantum channel. So in the previous example, I was discussing that eigenvalue for that particular classical channel will log 2. So that was then for majority vote, that's the number that comes out. But I could take other things. So in summary, what happens is that the local UV errors, or K local UV errors, do not, I guess I have to put significantly disturb the IR physics. And as you flow towards the IR, they get weaker and weaker.
Just one question here.
Yes.
So the stage 2 will depend on the eigenvectors of the channel of this
Yes.
isomet or this W channel. But the stage 1, does it depend on W, or simply depends on the length or the extent of this operator?
Just the support. In the very first stage, the operator does
support.
not get weaker. Only the support shrinks. That's important.
Yeah. But the shrinking rate is simply dependent on the light cone, the overall.
Exactly. There's an emergent light cone. There is an emergent light cone. Exactly. Precisely. So this is to be compared with holography. So in holography, what we have is something like this, right? There are these RT surfaces, right? So if you insert some sort of a non-local operator here, right? This non-local operator basically only affects things up to here. If you insert something here, this non-local operator does not do anything to the encoded information. So if you encode, sorry, I think this is a bad drawing. If you encode your operator here, then this is the K local error that you inserted. This error does not do anything to this. Now in Mira, what happens is that, so it just means that, basically what happens is that, so let's do RG. What happens is that in the next scale, the support of this guy has shrunk. In the next step, the support of it has shrunk. And at some point, the support reaches a point. Now here is in renormalization, in holography, you don't really have the story of the largest eigenvalue anymore. Over there, you immediately commute. So if you have a local operator here, oops, if you have a local operator here, it immediately commutes with that operator. But anyway, let me not just push for this. This has to do with the details of complementary recovery, and I'm actually going very far behind in my discussion. Actually, how many minutes do you have? How much time do I have? Because I have not
how much
even
time you need? How much time
well,
you
you
need?
know, I'll just, well, if you give me an estimate, I don't have to finish it. I'll just stop whenever I'll stop.
Okay. I mean, certainly 15 minutes more or something. That's
Oh,
fine.
okay. So that's more than enough. All right. Thank you so much. All right. So now let's talk about, I just said, do not significantly disturb. So let's try to be a little bit quantify this. So to quantify this, we have to do approximate quantum error correction. And approximate error correction, has been it's a well-studied topic in quantum information. There are conditions for it. So let's say you have a bunch of state, you pick a bunch of states psi I and the Hilbert space of HIR. We're going to pick these states to be provide an orthonormal basis, and this encoding map embeds this system, this IR states, in the UV Hilbert space. So the embedding of it becomes the code subspace. Now we're working with a code subspace. The conditions, the necessary and sufficient condition for approximate quantum error correction is that if you pick any two states, encode them in the HUV, then a local error in this basis is diagonal with a coefficient that does not depend on which state you talk about, plus a small correction. So this is so if I drop this small correction, this could be translated to the statement that W, sorry, I think I got my W's wrong. No, that's fine. This becomes something like this. That this is basically yeah. Let me not. I want to write it as projection. Yeah, I think this becomes proportional to projection. That's what happens.
But this is very similar to this eigenstate thermalization hypothesis, right?
So exactly. So eigenstate, very good, very good. So part of this work was inspired by that. So it's known that eigenstate thermalization hypothesis leads to an approximate error correction code. This is a work of Fernando Brandao and friends from 3-4 years ago. And the idea is precisely that they noticed that eigenstate thermalization hypothesis is literally the approximate error correction, quantum error correction condition. Over there, these epsilons are exponentially suppressed in entropy, right? So your code subspace is, you're looking at UV, you're looking at very high energy states, right? Your code subspace is the microcanonical ensemble of large energies, right? And you then, for such a system, local perturbations could be corrected. Here we're in renormalization group. We're looking at a very different regime. We're looking at infrared states. I want to make a similar statement, but proving something like this is going to be what nails down approximate error correction, and we're gonna do that. I don't, well, I'll at least code the result. Now let me just say one more thing, which is very important in this story. What we would like is not just quantum error correction. We would like local error correction. Because what we would like to do is a situation like holography. We would like to encode a bit here, qubit here. Now, a qubit here survives if you erase some region A, if you act with whatever error here, but also it survives if you act with anywhere out here. So this means that your qubit is sort of essentially encoded really in this region. Let's call this B. That's where your qubit is encoded, right? So why is this important? This is important because if I want to have a picture where I can insert more and more qubits, encode more and more qubits, right? So if my goal was to encode a single qubit in the infrared, then I didn't need to talk about local error correction. But if I want to squeeze a qubit here, then go ahead and squeeze another qubit here and squeeze another qubit here, I need local error correction. So this is going to be essential for us. So we would like the errors here to be correctable and the errors out here to be correctable. Are there any questions about this part? So in Mira, I guess one thing that I should say is that this paper of Kim and Castoriano proved this with some epsilon and deltas, and that dependent on the dimension of the local Hilbert space and how many layers you go up, right? So for a particular size of B, you construct these things that are called, these inequalities that are called the trade-off bounds, that tell you how the size of B scales with how deep in the, how many layers you've gone in on local sites, the dimension of the local Hilbert space. All right. So next, what we would like to do is we would like to do this in quantum field theory. So in the remaining few minutes, I'll discuss that. And this is going to be to just be parallel, to work out an example that's exactly parallel to what we just discussed. We're going to do continuous mirror. Now, I don't have to do this. I can do renormalization group in the sense of Polchinski, exact RG in Euclidean, using Euclidean path integrals, and a similar story holds over there. But I started motivating my story in the context of real space RG, where things are a lot more intuitive. Therefore, I'm going to push this, work out an example in the context of continuous mirror. So continuous mirror was first introduced by these authors, and later worked out in various examples. But the particular example of continuous mirror that I'll be working is this was sort of discussed in this paper of Hu and Vidal. So there are limitations to continuous mirror, as opposed to mirror, were discussed as renormalization group, real space renormalization group for arbitrary quantum field, arbitrary many-body quantum system. Mirror really is understood for free field theory, perhaps with some perturbations, maybe perturbative field theory. So the non-interacting the fully interacting, strongly coupled systems, nobody understands how to do sim-mirror for. I think that's the first statement. Now there are proposals, an analogy with holography, but we're going to discuss that. So to understand the details, let's just stick with a very simple example, which is free relativistic boson in 1 + 1 dimensions. So we have field operators phi of x and pi of x, and they satisfy this commutation relations. I'm going to do canonical quantizations because I have I was to draw the analogy very well with the Schrodinger picture. I was talking about the evolution of wave functional. So it's easier to work in the Schrodinger picture. But we'll actually switch to Heisenberg. We'll go back and forth because the Heisenberg has advantages as well. All right. So what is the idea? The idea is that we're going to set up the variational ansatz. There is a state that we're going to call lambda in some infrared. This state lambda is an unentangled state. At each point, it's just a vacuum of harmonic boson at each point, and you've tensored them. Of course, this state is completely irrelevant to relativistic quantum field theory. It only appears in non-relativistic quantum field theory, right? But it's our starting point. We take this and we evolve this using this unitary that that basically is supposed to do for us what we these isometric encodings and like successive isometric encodings and states of different scale. So if we run, so the operator that we're evolving with, this is the analog of that isometric embedding. There will be here, as opposed to the previous case where it was an isometry, this is going to be a unitary. and there will be two elements to it. There will be L, which is a non-relativistic scaling operator, and then there will be quasi-local entanglers. So remember, our Mera had these V's which basically what they did was scaling, right? And then there were the operators used that I called disentanglers. I call them disentanglers because that's usually we think of it as going up the chain. But if you think of it as going down the chain, it would be entangling. So these are the analogs of the U's, and these are the analogs of the V's, right? So here, this layer is like a two-layer thing. This is the L, and this is the K. All right. There is something. There are many various coarse graining schemes you could pick. As we were just for example, in the classical story, we said that we're gonna do majority vote. Here, there are many different things you could do. A particular coarse graining scheme called Magic Chimera. It was introduced by Gifford Vidal because it keeps everything analytic. So you basically what you do is that you suppress the UV modes. So you give this profile. So these disentanglers or entanglers entangle with some sort of a profile, right? Instead of, so in Mira, what we had was that these were entangling just adjacent nearest neighbors. Here, there is some sort of width for their entanglement. Anyway, what you need to know about this example, I'm gonna code the results, but like there are a few steps that are important for this. Under the CMIRA, what happens is that you get a vacuum state at each energy scale at each cutoff lambda. Now this vacuum state is annihilated by some is annihilated by a bunch of annihilation operators which relate these relations with canonical with the field and the conjugate momentum. So what you obtain is that after you solve it for your CMIRA, deep in the UV, your system looks like a gapped system, as was suggested by this. It looks like a gapped system. And deep in the infrared, you recover the modes, the CFD modes, right? As there should be a case sitting here for the creation and annihilation operators in the CFD. So the theory, what CMIRA has done is that it has taken the CFD and it has deformed it, but at some scale lambda with an irrelevant operator that breaks the Poincare invariance, and in the UV flows to a fixed point that is just gapped. Now we said all this to talk about, now that we went through all of this, we can go to the Heisenberg picture and we find that there are these symplectic transformations that will take the field and move you up the chain or down the chain. So these guys are exactly like the analogs of moving renormalization of operators in CMIRA, right? So these are some, before we had W's here, now we had V's. These are unitaries that move you up and down. And their action is very, very simple. If I look at the momentum modes, it's just simply this. But if you look at what they do to a local field operator, it takes a local field operator and replaces it with some sort of a profile. This profile has width lambda. So a local operator, as you flow towards the infrared, it becomes wider and wider in a sense, right? As we expect from real space RG. These are all intuitive things that should hold and come out of calculations nicely. All right. So I guess I'll have to wrap up very quickly. So, so just to do to prove the strain of approximate error correction, what we would like to do is that we would like to have a code subspace. So the code subspace is going to be the vacuum, and one of these coherent states constructed from the RG flown field operator. So yeah, let's just skip these calculations. What we want to these are all to check that this is a legitimate code subspace. what you find after the calculation is done is that you find that there is an approximate error correction code. So I talked about the code subspace looks like a qubit at each point, because I either have vacuum or I have this coherent state at that point. So these are the +1, -1 of my qubit, and I have a qubit at each point. This is my physical Hilbert space in a sense. So I'm calling such a state S lambda of X. And we would like to look at the matrix elements of a local operator at some large UV scale in these matrix elements. And then what you show is that you work out in Symmetry and you prove a statement like this. This is exactly what we need for approximate error correction. And these small corrections that are suppressed by the scale, how far you are separated in scales, controls that how good of an error correction code you have.
Sorry, what is this S labeling?
Sorry.
The S, what is it labeling?
Sorry.
The S, what does it label?
Oh yeah. So S is this. So I have at each point I have a S is like a qubit at the point X. Then two states of it is vacuum or a particle or a coherent state at that point. Right? At each point I'm mimicking a qubit because the Hilbert space is it's a boson, right? So it's infinite dimensional at each point. It's messy to work with. I'm just simplifying my life by saying I have a qubit at each point and I'm looking at that subspace.
Okay.
Right? So this is just to make everything closer to the examples that we're discussing, right? So of course there's a lambda index here because I put the coherent state with the operator flown at that scale. So yeah, this is.
I'm just what I don't understand is this is a delta SS prime there, right? Which is so there shouldn't there be an X level 2 here somewhere?
Oh yeah, for sure. But I picked them to be all at the same point. So you see, yes, you're absolutely right. So what I'm looking at is this setup like this, where I've created an excitation at point X equals 0 with this width lambda, right? Now I'm exploring an error that sits exactly at that point. Now this equation will continue to hold as long as, if I put this at Y, as long as Y minus X is smaller than lambda. So I can move this error around. For simplicity, I was just writing it. I just didn't want to make the equations have more arguments. But if I move this error within this region, I still have a nice protection.
I see. Okay, now that was what my confusion was. Okay.
Yeah. I'm just, for simplicity, I'm just putting it so that this side of the equation doesn't have X and Y's.
Okay.
Now, on top of that, you actually have local quantum error correction, which means that you could correct for operators out here as well, as we would like. So I guess, I'm out of time, so I'm not going to discuss the details of the calculation, but the way the calculation is done is by constructing the reduced density matrices for regions A and C in these excited states that we have been discussing, and calculating the fidelity, which is a measure of distance between reduced density matrices in these states, and proving that the fidelity is small. That's like an equivalent way of discussing approximate error correction. So those are the technical details of it that I guess I'm jumping over. And let me just jump to the conclusion. So in conclusions, we discussed that low energy states of a local many-body quantum system in real space renormalization group form an approximate classical or quantum error correction code where noise is irrelevant local operators. And we give examples from classical spin systems, Mera, and Symmetry in quantum field theory in 1+1 dimensions. But this example generalizes to massive quantum field theory in arbitrary dimensions. Thank you so much.
Thanks for this beautiful talk. So we should have questions. Please ask questions.
Yeah, this is not so much a question, I guess, as it's more of a observation, comment. So Vladimir Korepin back in 2002, he showed that if you consider systems in thermal equilibrium, and he used the example of various kinds of different spin chains to illustrate this, that in thermal equilibrium, the state satisfies the error correction criterion, right? So the statement is that you can think of thermal equilibrium as a state in which error correction is happening in some sense. Now, I mean, I'm not sure what the relation of that would be to.
So
to
actually,
your work.
a quick question: when you say thermal equilibrium, at what temperature? High temperature or low temperature? Because the very first question I would have is that this is supposedly approximate error correction. There won't be this level of generality. There won't be exact error correction. So what controls the size of the errors? Is it large beta or is it low, small? Yeah. Because if you go towards high temperature, small beta, that comes closer to the story of Eigenstate thermalization hypothesis, right? So that's a modern understanding of it. And the regime I'm discussing is sort of the opposite regime, right? I'm discussing the low temperature regime of it. And I'm working out in various examples, the error bars and what controls the approximate error correction. Actually, it would be lovely if you could share. I was not aware of this work. If you could share with me the reference, I will definitely look into it. But I think it seems like some of the ideas are already appearing there.
Right.
Thank you.
I have a question about the seam error actually. So you're saying that you can also it mimics holography in some way. That initially you said the discrete mirror does not, but the seam error you say that somehow is mimicking holography. But is it restricted to only this specific kind of local space, or is it's a very? So I didn't follow that.
Yeah. So it's a very good question. Okay, so in Symmetry, what happened? So what you don't have in Symmetry is complementary recovery. The very first paper we wrote with Choi and Keiichiro was all about the discussion of complementary recovery. So the whole paper is about that. So let's say I'm going to draw Symmetry in a suggestive way that looks like ADS CFT, right? So what happens is that under RG flow in ADS CFT, you have this feature that an operator with this support, for example, maps to some local operator of this support, right? Now, what is important is complementary recovery, which means that if you look at an operator like this and bring it down, it will map to something like this, right? This is what is lost in Symmetry. In general, in quantum field theory, what happens is this. So when you if you bring this down, there will be an overlap. So there will be an overlap, which means that you can't encode. Your code is not as good. You can't squeeze in. So if you want to encode properly here, what you could do is that you could encode a qubit here and then encode a qubit here, so that down the chain is like this. You have to leave these gaps. These gaps are exactly the things that get to the bottom of this. How many? I didn't discuss this but how many qubits can we squeeze next to each other? These have to do with these trade-off bounds, right? How good of a local error correction code it is, right? How good of a local error correction code it is.
Great.
Yeah, so this is the distinction, and it's the same story in Mira as well, actually.
Okay, so maybe I will have some offline discussion with you on this.
Yeah, for sure.
Okay, good. So let's see if there is one more question, and then we can move to an offline discussion, a short offline discussion. Okay, if not, then let's thank Nima again. And so please visit Chennai and also goes to Shoy, visit us, and yeah. So